Welcome back to ECE 442-542. Homework 4 is due on Thursday evening, and that will be the material that will be on exam number 2. Exam 2 will be covering homeworks 3 and 4. Exam 2 is a week from Wednesday. As a reminder, tomorrow office hours have been rescheduled. Because I'm eliminating an hour, I'm giving you 15 minutes extra, meaning you have from 2 to 3:15. My 2 o'clock was canceled, but my 10:30 was interrupted. So we won't have office hours tomorrow morning at 10:30, but they will happen at 2 o'clock. And that's only a one-time event. That's not for the rest of the semester. Exam number 2, I'm presupposing or simply assuming that what worked last month, might work this time. A review session on a week from tonight, starting soon after this class finishes, Monday at 7. Next Monday at 7 is when we will have the review session for exam number 2. What I want to do today is talk about realizing some of these systems that we've now created. We can put these low-pass filters or any kind of filter that we want into a discrete time realization or into a difference equation. And let's just do that for a low-pass filter as an example. We can then see that occasionally we might need to have a constraint on the implementation, meaning we may not be able to immediately measure the input and inject that into the output of our expression, meaning the input at time n may not be available when we're trying to generate the output at time n. And for that reason, we will have to do some changes to our 0 at infinity development. Then we will sort of move into new territory, but it will sort of be, I think, a review or a help to what you're doing now, and that is translating. We're trying to move, now we have all this modeling available to us. Now I think we're ready to start controlling or designing controllers, and to do that we need to learn some design rules or some ways of specifying pole locations in the z-plane that would be desirable or that we would like to have happen in our closed loop system. And that's what I'm trying to get into with this design specifications and second order poles, meaning we probably are going to establish our design specs based on just a second order system, and then all the other poles will be faster than that. That means they will be closer to z equals 0. That's really, really fast in the z-plane. When you put everything inside this very small region in the z-plane, those poles or routes or modes would be much faster. And the dominant behavior would be specified by those 2 dominant poles that are determined by your design specifications. Here's just a recap of where we were last time with the discrete equivalent technique concerning pole 0 mapping. We factor our transfer function h of s, which might be a controller, it might be a filter. We factor that into pole and 0 factors. Then we map all the poles into the z-plane using z is equal e to the st. We map all the zeros, finite zeros, into their factors using z is equal to e to the st. Then if we have infinite zeros, and when do we have infinite zeros? Or what defines an infinite zero? If I give you a transfer function, capital H of s, can you tell me immediately by looking at that transfer function how many infinite zeros you have? The answer is flip a coin, right? Yes or no. And if you tell me an answer, why? Yes. So now you're looking at, you see what's the denominator order? That's the number of poles you have. You look at your numerator order, that's the number of finite zeros you have, and you look at that excess. How many more poles do I have than zeros? If that happens, let's say it's a fourth order denominator and a second order numerator, your pole zero excess is 2. Maybe that was a bad example. Let's say you had a first order numerator and a fourth order denominator. Now your pole zero excess is 3. You have 3 zeros at infinity. Those then would each correspond to a z plus 1 factor. Now in your numerator you would have a z plus 1 cubed in your discrete equivalent using this pole zero mapping. Unless we do something or need to do something different, which we'll show in a minute, if we have an implementation constraint or an implementation issue. Then we match the gains. And where do we match the gains? It depends, right? So that's another answer you can always give, maybe. It depends on what kind of system you're beginning with H of S. If H of S is low pass, then where are you matching gains? Probably at DC at low frequencies. If H of S was high pass, then you would be at high pass at the high frequency. If it was something else, like a band pass, maybe you're matching the gains in the passband region. So it depends where you match the gains. Here is our example from last time. Again, I'm going to just sort of go through this quickly so that you remind yourself of what we're doing and why we're starting with what we're starting with. We have a low-pass filter. It's first order. Our pole zero excess is 1. Our DC gain is 1. And we have a pole at minus A. That you should be able to say immediately if somebody gave you that information, or if they ask you to design a low-pass filter in an interview, you can say, okay, is it okay if I give you a first order? And then you can just write this down and tell them all about it. Then we map that into a discrete equivalent by taking the pole and placing that pole at e to the minus at. We had one infinite zero. That means we have this one factor, z plus 1, in the numerator. There were no finite zeros to map. And then we matched the gains at DC, and that's what that leading expression is in front. That's the gain needed to give this a DC gain of 1, that g sub d of z, and that's g sub d of z evaluated at z equal to 1. That's where you would check its DC gain. Now let's put this g sub d of z into the time domain. Let's create a difference equation. So now I could code in, or you could code in, an algorithm that would spit out a low-pass filtered waveform based on whatever you had selected for your bandwidth or passband interval from that pole A. And you would have to select your capital T. But we will probably just go ahead and keep those as variables. Let's now create a difference equation. So now we have this g sub d of z, which we could say is relating an input e of z to an output u of z. And we said that that was this gain times the infinite zero factor and the pole at e to the minus at. If we take this into the time domain, we can simply multiply both sides through by z minus e to the minus at, and remember that z in the frequency domain is like an advance in the time domain. And we now have, or maybe what I want to do, why don't I map that differently so that I have delays and not advances, and how could I do that? I can always multiply something by 1. So now I could say, oh, let me multiply that by 1. So maybe before, oh, I'm going to really frustrate you now, aren't I? I'm going to cut my paper and paste it back together with a little space in between. But you can quickly erase time domain and write it further down. We can now say that u of z over e of z is this 1 minus e to the minus at over 2 times 1 plus z to the minus 1, 1 minus e to the minus at z to the minus 1. Now I can multiply both sides by this 1 minus e to the minus at z to the minus 1 and by capital E of z to take that into the time domain, and I end up with u of n. And let me take that minus e to the minus at z to the minus 1 times u of z onto the other side in one step, which means I now have e to the minus at u of n minus 1. And I now have something that is a scaled version of two terms involving e. One is e of n, and one is e of n minus 1, based on that 1 plus z to the minus 1 in the numerator. And they're both scaled by this scaling factor. When I fix a and t, this is just a number. And I now can multiply that by e to the n plus e to the n minus 1. And if we think about what this is doing in terms of an algorithm, u of n, this we could say is the output of our operation. E's are inputs, U's are outputs in this particular way that I've defined the transfer function. This is the output at time n, which is the present time now, is what that's supposed to be in terms of here is the output one time step before or at time n minus 1. So I would now have to remember that in some register. I now remembered my previous output and I've stored that. Now at, let's say, time n minus 1, I scale that by e to the minus at. I now have this gain somewhere stored in a memory location, and as soon as I measure e of n, I could add e of n to e of n minus 1 and scale by this, add them to this, and then at that n time I spit it out to my system if I needed to do this in sort of a real-time fashion. These two terms, this is the input at time n, which is now, and this is the input one time step before. Meaning if you were now doing this and you were getting input information in real time, you would have to measure the input now and then quickly do some computation, maybe you have already scaled e to the n minus 1 by this gain, and maybe you've already added that to this e to the minus at u of n minus 1. You now have this partial sum. Your input comes in, you measure it, you scale it by this number, you add it to that partial sum, and now you generate your output. That may take a fair amount of time for that to happen. And that's what this new implementation constraint that I'm going to talk about next tries to accommodate. Meaning maybe by the time you measure the input, scale it, and then add it to that partial sum, maybe that takes you 50% of your sample period to do that. That's probably too long. So you might want to say, why don't I just assume that I no longer have this input at the present time or now? Why don't I try to design my algorithm so that I am only using inputs one time step before? That's the implementation issue or constraint that I want to talk about now. Is that sort of clear what's happening here in terms of an algorithm if you were doing this in real time? How you might implement this? The implementation issue is now involving these zeros at infinity and what I do to those when I don't have the input available at the present time. So zeros at infinity and when the input is available. So here's a very wordy way of what I just tried to describe. If the input at the present time, which I'm saying t is equal to little n capital T, if that's effectively not available, if we can't measure that and quickly generate an output, then we're going to assume that the input is not available at the present time. It's not available in the implementation of this digital system. In our case, that was a low-pass filter. If that's the case, then what we want to do is remove one of those zeros at infinity. If we had two zeros at infinity, we would actually just introduce one in our discrete equivalent. If we had four zeros at infinity, we would take one away and we would only implement a z plus 1 to the cubed factor. We would remove one. That's what I'm trying to say. Then one of the zeros at infinity needs to be mapped not to z equal minus 1, but actually to infinity, which really says just remove it. One of those factors needs to be mapped to z equal infinity. Another way of saying that is, and now this, I need to make sure the brackets are correct, only map, let me put a curly brace and then a parenthesis, the number of zeros at infinity minus 1, that's a number. So if I had four zeros at infinity, this now in curly braces says I have 3. And I only mapped 3 of those through that z plus 1 factor in my resulting G sub D of Z. So let's look at that earlier example that we just worked. Whoops. This low-pass filter. Let's create a new discrete equivalent for that. So now it's going to be barred. It's now a G sub D of Z bar. The pole maps the same way as before. I had a 0 at infinity, but I just said reduce that by 1, so that means just get rid of that factor. And now I'm going to have a new gain, let's say a K bar. This elimination is I want to remove So this example might be misleading. You might say, oh, just get rid of all the zeros at infinity. No, you just remove one of those factors. But this one only had one factor, so we are removing all of them in this example. Is that clear? So if that was z plus 1 squared, I would just take z plus 1. Reduce the power by 1. Now I need to find k bar. And how do we do that? What kind of a transfer function did we start with? What was g sub c of s? That was a low pass, wasn't it? So we're matching gains at low frequency, or DC. That means that we want to look at g sub d bar of z at DC and set that equal to the DC gain in the continuous time case. And if we look at g sub d bar, that's this k bar over 1 minus e to the minus at, and that's equal to 1, a over a. And that's pretty easy to solve for k bar. Now our k bar is 1 minus e to the minus at. Before, our gain was that divided by 2. And this now says that our result writing it maybe in this expanded form so that it's clear that we no longer have, we have one fewer z plus 1 factors, and our gain now is a little different than what it was before. This is now our g sub d of z. If we take that into the time domain, we now get a slightly modified difference equation. What do we have? Well, I'll do the hard part. We have a u of n. Where did that come from? That came from this term right there, didn't it? If I cross multiply, in this case I'm only cross multiplying by 1 minus e to the minus at z inverse. That scales u of z. E of z is getting scaled by what's in the numerator. But there's really only one term in the numerator. That parenthesis, or that term in parenthesis, is just a number. once I fix A and T. And so now I have an e to the minus at z to the minus 1 with a minus sign on the left. I want to move that to the right-hand side of the equality. So I add that to both sides. I now have e to the minus at one time step earlier. And what do I have now for the input term or terms? Now I have a gain scaling the input one time step into the past. And I don't need the input at the present time. E of n is no longer there. And that's because I eliminated one of those zeros at infinity, or eliminated that one factor z plus 1. Is that clear? So you want to compare this time domain expression with this new implementation constraint with this implementation. In this one, our gain has been changed, and that sort of makes sense. Here we had two inputs, and if they were equal, they would get canceled by that 2, and they would get scaled by the same scaling amount. So if these converged to an equal number, then this is going to look the same as that. But until they become equal, this one now is going to be different, and we don't have to have the present input value to generate the present output in this second implementation constrained approach. And that was because we then removed one of those z plus 1 factors. Questions on that or what we were doing? Exam 2 material is above that line. Now don't phase out on me, because this will be useful information, I think, for inversely transforming discrete equivalence, but it will definitely be of importance when we start designing controllers. Let's now do design specifications. And how those relate to second order pole locations. How many have already had a classical control class? Few? All right. Maybe you will be bored, or you can help your neighbor understand this after I confuse everyone, okay? So I'm going to go through this a little bit quickly, but I hope that it makes sense. And since I prefaced it with the way that I did, in terms of confusing you, I'm sure it's going to really make everyone happy. So you never tell your audience that, oh, I'm going to confuse you. Then you're going to go, any slight stumbling block, you're going to go, well, he didn't do a very good job of this. So let's all just get this, okay? Continuous time material. First, what I want to do is start with a second order system, and it's going to be underdamped, an ideal underdamped second order system. And I hope you already are feeling what I'm saying. Or here, just go to your car and start it bouncing, and then it will just shake for a little bit, probably not very long, unless you need new springs. But it will just bounce, and then it'll damp. So you have a decaying, exponentially decaying system. Or you have this mass spring damper system that we've talked about. The transfer function for an underdamped second order system can be written many, many different ways. One way is to write it in terms of the natural frequency omega sub n and what this new zeta value, a damping ratio, zeta, or we could also write it in terms of real and imaginary components in the S-plane, where it has a real component of sigma, minus sigma into the S-plane, and an imaginary component omega sub d. Now we have S plus sigma quantity squared plus omega sub d squared. So we have a damping amount sigma, and we have a damped frequency omega sub d. If we wanted to locate those in the complex S-plane, they're always going to come in pairs, and they're going to be complex conjugate pairs, and a lot of times I won't even show this bottom. But we're always going to assume we have real coefficients in our transfer function. And now we can identify certain locations in these parameterized representations. Here, this distance into the complex S-plane is the damping amount, sigma. That's their real part of these poles. Or that's zeta omega sub n in value, numerical value. They have a imaginary part equal to the damped frequency, omega sub d. And that damped frequency, that's DAMP, if I'm not enunciating properly, but that's the damped frequency. So there's a P on there. Omega sub d is related to the natural frequency, omega sub n, by this damping amount, square root of 1 minus zeta squared. And the natural frequency, that's supposed to be a radial line, is the distance between the origin in the S-plane, S equals 0, and that pole location. That's the hypotenuse of this right triangle. It has an adjacent side, and we're going to call this angle theta, which is different from theta sub d. So when I start talking in the z-plane about angles theta, I better subscriptum d. It's not the same as this angle theta in the continuous time S-plane. What else do I want to color on here? So this pole is at a value minus sigma plus j omega sub d. We then have, or we could write it in terms of this damping ratio zeta and natural frequency omega sub n. Terminology-wise, sigma is what I'll call the damping. Zeta, this Greek symbol, is the damping ratio. Omega sub n is the natural frequency, and that's, again, the distance that pole is away from the origin. And we have the damped frequency, which is a reduced amount. That's the horizontal, or that's the vertical distance. Associated with those poles. Meaning, as we could swing this set of poles. That's supposed to be a semicircle. And when we would get up to this point, what is zeta? When our poles are right on the imaginary axis, when we do not have any damping. If we don't have any damping, our damping ratio is 0, so we have just an oscillator. We have two poles right on the imaginary axis. If those poles actually both swung around here by increasing the damping, then zeta is equal to 1 when they become real, two real equal poles. And we're going to, the undamped or the underdamped case is when we have a zeta value between 0 and 1, meaning this angle theta could be either 0 degrees, purely real poles, or it could be 90 degrees, purely imaginary. Now, for that, what we want to do, this is now our second order system. We want to now apply a step to that, 1 over s, a unit step, and generate our step response. I probably should have made that larger, but that's what we now have. We basically hit it with a step, and it starts, depending on how much or how little damping there is, this is going to peak a lot or not very much in this underdamped behavior. And we can identify many different points on this. This is now y of t. That's the step response. Let's just assume, for generality, that this is the final value. In this case, it's going to be 1, but I'm just going to say generically we don't know. We may have some gain in the system, and so we might have a non-unity final value. This is where our response peaks, so we'll call that the time to peak, or the peak time, T sub p. That's the value of the response at that peak time. And then we also could have, so I didn't draw this very well, but let's say this is now our 1% tube. And we'll call that our settling time, T sub s. That's when the response first gets into that 1% tube and never gets out of that 1% tube. That's our settling time, capital T sub set. I think I've defined what I want to define here. Meaning, keep track of T sub p. This is our peak time. Maybe in this class we'll just agree that when I say settling time, let's just agree that that's a 1% settling time, and we'll just say that's 5 time constants, which 5 time constants actually is a little bit more demanding than a 1% settling time. And what else? This is now our maximum value, y sub tp, and y sub fv is our final value. Y of t, if we needed to compute that, now I'm going to try to justify some of these expressions that we will create or just write down. That's the inverse transform of capital Y of S. But we've said that the output is just this second order underdamped system G of S hit by the input step response capital U of S. So it's just GU. And if I wanted the time to peak, if I ask you to find that, and now just sort of transport back into a calculus class, hint, hint, and if I'm saying, how do you calculate the time to peak? How are you going to find this T sub p if you know Y of t? If you know a formula for y of t, how can you find t sub p? You differentiate y of t and set it equal to 0, don't you? That's where it hits its maximum. So if we wanted to do that, we would say, oh, just differentiate y of t, this expression, set it equal to 0 and solve for t, and that's going to give us our peak time, t sub p. That's the idea or the concept. But another way to think about the derivative of y, if we already have capital Y of s, so now my prime and dy dt, hopefully it's clear what I'm meaning by all of this. The derivative of y we could find by sy of s, an inverse Laplace transform. But we already have s there. G of s, I'm going to mix my two notations here. That's G of s in square brackets. I have a unit step, which now allows me to simply cancel those two s's. And I need to inverse Laplace transform this to give me a y of t. And do you remember what's going to happen when I inverse Laplace transform this S domain transfer function? Where are my poles? Come on, my memory's not that bad, Dr. Tharp. You just told me where they were, right? They're complex in general. If I have complex poles, what is going to happen when I inverse Laplace transform something with complex poles? I'm going to have exponentially damped sines and cosines, aren't I? And in this case, I do not have an s in the numerator. That means I don't have a cosine piece. I just have the sine piece. And if I look at this, I could actually sort of force this to have the structure I want by scaling that by 1, because I need, in terms of an expression, omega d over s plus sigma squared plus omega sub d squared, and that's my pure sine, exponentially damped sine. Meaning, I can now write this derivative of y as this scaled version, omega sub n squared over omega sub d, and now what's left is the pure exponentially damped sine. And now I said I wanted to set that equal to 0. But I want this to give me a non-trivial answer, so I want the first time after t equals 0, when that equals 0, to give me this non-trivial time to peak. And what's that going to imply? I now want because e to the minus sigma t, that's non-zero, isn't it, for all values of t. So I don't need to worry about that. This is just a constant, omega sub n squared over omega sub d. I don't need to worry about that. The only time that expression is going to be 0 beyond t equals 0 is when sine of omega sub dt is equal to 0. And this is why you took trigonometry whenever you took trigonometry. 7th grade, or was it 8th grade? Whenever. You now have this guy, and what does that imply? What's that imply? And if I just go ahead and say I want t to solve that, make that equal to 0, that's going to be my time to peak. Let me just go ahead and subscript that here and say, okay, I'm going to call that my t sub p, omega sub d t sub p. The argument now needs to equal pi, and that will be the first time after 0 that that equals 0, that expression. And now I can solve that for my peak time. My peak time is now pi over omega sub d. So if I say, give me an expression for the peak time, that's now just pi over omega sub d. And what was omega sub d? That's the vertical component of those complex poles. So the more vertical you have on those complex poles, the faster or the quicker your time to peak will be. And if you wanted to, if somebody gave you a time to peak, they would say, what's omega sub d have to be? Well, if they've given you this, you can solve for omega sub d, because pi you know. You guys are going to have to enjoy the day after, the 2 days after our exam, right? Our exam is 3/12. Friday is 3.14, so that's pi day. You'll need to enjoy that before or right at spring break, okay? But we now have a way using that pi. I know that choked everyone up, didn't it? But we now have omega sub d. If we are given t sub p, we can solve for omega sub d. We now can say that omega sub d is pi over t sub p. And if somebody gives you a really, really tiny time to peak, that says omega sub d is going to be big. So this is another way that you can use that relationship. Now, we have a time to peak formula. That's based on our continuous time terminology. We can also look at, based on this second order response, we can figure out our percent overshoot. And we'll base that on our final value. We say, how much beyond the final value did you go? And use that to give us our percent overshoot. Our percent overshoot formula then is our maximum value minus our final value normalized by the final value times 100%. Now, if you replace, so that's how you could, if you were given this time response, you could physically compute your percent overshoot. Your measured percent overshoot you could calculate. Or if somebody gave you the equation for y of t, we now know what the peak time is. The peak time we just computed to be pi over omega sub d. We could plug that in for our time and obtain that the percent overshoot in terms of zeta is now 100 e to the minus zeta pi over the square root of 1 minus zeta squared. That's our percent overshoot in terms of zeta. And zeta is what? Between 0 and 1 to give us our percent overshoot. Now, if you have this and you enjoy algebra, maybe somebody says, I want my system to have a 10% overshoot. Well, you could sketch this for different values of zeta and figure out what percent overshoot is, and you now have this graphical depiction of this relationship between percent overshoot and zeta. Or you could simply solve this expression for zeta. And if you do that, and you should all have this memorized if you took the classical class, you now have the natural log of P over 100 squared. So if you say I need a 20% overshoot, You now have the natural log of 0.2 squared divided by pi squared. And what's pi squared roughly? 10. So pi squared is about 10. So that's 10 plus natural log squared of percent overshoot over 100. And then don't forget to take the square root. That's now how you could numerically calculate the zeta value, your damping ratio, if you're given a percent overshoot. If you simply found a curve in a textbook, it has this decay. And over here, at about 0.7, and we're going to find that that's the sweet value that we like, or that I like, and it's sort of this nice compromise. That corresponds to that theta angle of 45 degrees. So you have an equal real part and equal imaginary part. That gives you a percent overshoot of 5%, 0.7 for zeta. So this is our zeta axis. 0.6, and I'm not going to be able to sketch this very well, pretty poorly. But 0.6 is about 10%. And this really gets pretty bad pretty fast. At 0.2, it's a 50%. The smaller zeta is, the more you're overshooting where you're going, but the faster you're doing it. There's always trade-offs. That's why you're doing the control, to figure out how to balance or determine how you want to trade these different competing objectives against each other. If I now go back here, and if somebody said, oh, can I relate theta to zeta? And here's where you use your trig. What's the cosine of theta? Adjacent over hypotenuse, by definition. Is that true? That's the cosine. That's the cosine of theta. But we already know what the adjacent is. That's zeta omega sub n. Our hypotenuse is omega sub n, and everything's going to fall out. That's why we've defined that theta. If you look at this, we could now say that the cosine of theta, so if somebody gave you your poles, you could determine that angle theta, and then you have zeta. Once you have zeta, you could plug it in to this equation to get your percent overshoot if somebody said, what's your percent overshoot? And this is all based on a pure two-pole system. It's an idealization, but it gives us something to start thinking about. Cosine of theta is, by definition, the adjacent side over the hypotenuse, but the adjacent side was the damping, sigma, zeta omega sub n, over the hypotenuse, which is omega sub n, and now you have zeta. So that now if somebody gave you a zeta value, whoops, you could now tell them what the angle theta needed to be, or this relationship between the real part and the imaginary part of your two complex poles. That's now our percent overshoot. What have we derived? Time to peak and percent overshoot. Now let's talk about one more, which is the settling time. We said let's deal with the 1%. And now I'm saying that's approximately 5 time constants, meaning if we had a mode that was e to the minus t over tau, a 1% settling time we're approximating with e to the, where t is now 5 tau. And if you compute e to the minus 5, that's going to be a number less than 0.00 or 0.01. It's going to be like 0.006 or something. But that's what we're going to agree is okay for a 1% settling time. That said, then we can say that our settling time, t sub settle, that's when this guy gets into that 1% tube and doesn't leave. That takes 5 time constants. But in terms of our damping amount, our damping in these exponentially damped sine and cosine expressions is just e to the minus sigma t, and this shows us the reciprocal relationship between our damping and our time constant. This says that we now, if we need a faster settling time, we need to increase sigma, and that does what? In our left half plane, that pushes our real part more and more into the left half plane. The further we push our poles into the left half plane, the quicker our system is going to settle. Is that okay? And we could also write that in terms of zeta and omega sub n. That's what sigma is. That's now our settling time. We now have three different ways of introducing design specs into a continuous time system or classical control setting. We could do our settling time, which now says that we have, if we solve that for sigma, we have 5 divided by t settle. Now let's say we had poles that were sigma 1 in, or maybe we had poles that are sigma sub 2 in. I hope it's clear then that if we want to decrease our settling time, we need our poles to have real parts that are further into the left half plane. That gives us a e to the minus 6 versus an e to the minus 2.4 t. E to the minus 6 is much faster than e to the minus 2.4 t. That's our settling time. Our percent overshoot now, if I give you a percent overshoot, you could compute zeta from that formula that I gave you. That was the natural log of PO over 100. And there your percent overshoot is in 10%, it's 10. 5%, it's 5. 30%, it's 30. You divide it by 100. Pi squared plus natural log, all square rooted. Zeta then is associated with this angle. If I want less overshoot, what do I want that angle theta to be doing? If you think of this as creating a pizza wedge, needed to get off the pi, but I wouldn't mind if it was a pi wedge. What do you want for percent overshoot? What do you want that wedge to look like? Bigger or smaller to reduce the overshoot? You need theta to get smaller, don't you? You want zeta to get closer to 1. You're wanting those poles to become more real. Reduce the imaginary part. So if we wanted to decrease the percent overshoot, we're moving that angle towards the real axis in the S-plane. And as I said before, a zeta value of 0.7 is a nice value, and that actually corresponds to a 5% overshoot. And that theta angle is 45 degrees. We've looked at settling time, percent overshoot. Let's now look at one more, which is the peak time. Time to peak was pi divided by omega sub d. Or, if somebody gives you the peak time, you can now calculate the imaginary component of your two complex pole pairs, or of your two poles that are complex conjugates of each other. In the S-plane, maybe somebody gives you a time to peak that corresponds to this vertical distance away from the real line. Or maybe they give you a different time to peak associated with this red dashed line. Now, according to this will give you a time to peak 2, and this one, let's say, gives you a time to peak 1. How are those two related? TP1 as a number is what relative to TP2 as a number? It's greater, isn't it? So here we have TP1 is bigger than TP2. If we want to decrease, our peak time, which I'm using lowercase t sub p, then we need to push our imaginary part further away from the real axis. That will decrease our peak time. Now, we have all of those images or pictures of the S-plane in our head, hopefully, for those three design constraints. Let's now map those into their Z-plane equivalents, or what that looks like in the Z-plane. Let's now translate these design specs into Z-plane pole locations. What we are going to use is our friend. Z is equal to e to the st. But S we can parameterize many different ways. One that we will use a lot is minus zeta omega sub n. That's the minus sigma plus j omega sub n square root of 1 minus zeta squared all times t. That's now our Z-plane location relative to an S-plane that pole, this is in the, let's say, the second quadrant in our complex S-plane, that has a real part of minus zeta omega sub n and an imaginary part of omega sub d. We can now write that as e to the minus zeta omega sub n t. I'm now distributing that sampling period through the two pieces of my exponential, e to the j omega sub n t square root of 1 minus zeta squared. And omega sub n square root of 1 minus this with that is just omega sub d. So this is e to the j omega sub dt. This we could say is just an r. So now we have r, e to the j, omega sub dt, but we could say that's r, e to the j, and there's my new theta. This is theta sub d, where theta sub d is omega sub dt, which now in the z-plane, in the s-plane we were thinking rectangular coordinates, sigma and omega sub d. Now in the z-plane it's maybe easier to think in polar coordinates, r and angle theta sub d. Now we have a pole here and its twin downstairs. This distance is now our r, which is e to the minus zeta omega sub nt, and this is our angle theta sub d. This pole is now r e to the j theta sub d. Now we know how this mapping is going to behave. Let's look at the settling time. And I'm hoping now you're thinking target practice. What? Well, maybe that will make sense. Now, when you're thinking settling time, well, let me not get ahead of myself. What did we have for the settling time concepts in the S-plane? If I said settling time, what are you visualizing in the S-plane? Moving further into the left half plane, and you want to now put boundaries up corresponding to vertical lines. You draw a vertical line, you say, I need to be to the left of that vertical line. Oh, I need more settling time. Well, then you need to put your vertical line further into the left half plane. You want it even faster? Keep moving that further and further to your left, into the left half plane. Meaning you can now have something here, which might be sigma 1, or it might be here. Sigma sub 2. We're now going to map that, those two, through our friend, z equal e to the st, and what happens in the z-plane? Let me just pick something, and let me say, now this gives me e to the minus sigma 1t. That gives me my radius, doesn't it? If I go back here, zeta omega sub n is sigma. E to the minus sigma t gives me a radius. If you fix sigma sub 1, a vertical line in the s-plane, at some location, that's going to fix my radius in the z-plane. So I could be anywhere on this radius away from the origin in the z-plane. And let me say that that's here. Wow. I didn't take an art class. This is now e to the minus sigma 1t. That's some radius away from the origin. Where's the red circle? I have to state what it is because you couldn't tell by looking at the sketch. These are supposed to be circles. Where is red relative to blue? Go Wildcats, right? Red and blue. May not be the right red and blue, but it's close enough. Where's red relative to blue? I got you distracted. It's inside, isn't it? E to the minus sigma sub 2, so now we are here, let's say. And now do you understand what I was meaning when I said bullseye? I'm thinking barbecue sauce now. Sorry. This is supposed to be a target, not a barbecue sauce. So a bullseye, concentric circles. If you want faster settling time, what do you need with your target? You need to be collapsing, getting closer to z equals 0. Is that making sense? If you're close to the unit circle, you don't have a lot of damping. Your settling time is going to be quite long. But as you collapse that, as you get your concentric circles closer or more in towards the origin, now you're going to have a better settling time or a faster settling time. In this case, we have, let's say, R1, which is e to the minus sigma 1t, or an R sub 2, e to the minus sigma sub 2t. So if somebody gives you a settling time specification, what do you immediately need to be thinking of? What should come to mind? Your ABCs, and you need to get all the way up to R, don't you? You need to say, oh, settling time R. I need to worry about being a certain radius away from the origin in the z-plane. If somebody gives you a settling time spec, you think radius in the z-plane. We've already talked about this, haven't we? Let's look at a cut. Whoops, that wasn't supposed to be an add. It's supposed to be an A. So let me change that. I'll start going to a web address or something. A. Send somebody an email through my lecture. Sorry. A. Let's say that you're given a settling time. Now you want to find the R, the radius. And if you needed to, if we need it, we could say t settle is some integer number of the sample periods, and I'll say that that integer number is capital N sub s. That's how many sample periods it's going to take before I have settled to 1% of where I started. And we've done this already. X at time N sub s, at the N sub s sample, if we're just worrying about the transient, is R raised to the capital N sub s times where we started. But if we're interested in the 1%, that just means 0.01 where we started. And we want to do this for a non-trivial initial condition. That's some value. We can divide that value out. And now we have a relationship between the number of samples to settle and our radius. Now, if we go ahead and use this relationship, T settle is N sub s T, then we could also rewrite that N sub s as T settle over T, which says now if we have R, N sub s equal to 0.01, we can now say that N sub s log base 10 of R is equal to the log base 10 of 0.01, which is minus 2. If I solve that for log base 10 of R, that's just minus 2 over N sub s, and I might use that again, so let me call that my star formula. And now R is what? I just solve for R, and it was base 10 logarithm. I can raise everything to the, or raise 10 to both sides, and I end up with R being 10 to the minus 2 over N sub s. Or if you had it in terms of t settle in your sample period, you could replace n sub s in this formula with that. And now you know your radius. For example, suppose somebody says, I want a 1% settling time of 60 samples. And now they don't even tell you what capital T is. They just tell it to you in samples. Well, you can just immediately plug that in. And now you have a radius for your complex poles. They need to live on or inside 0.926 to give you a 60 sample period settling time. Now, that was given a settling time, find the radius. What if you look at the other problem? Maybe somebody is giving you an R, and they say, what is the settling time for this particular set of poles? So now I could give you two complex conjugate poles in the z-plane, and I could say, what's your settling time for that complex set of poles? Then you need to find the radius, just the argument of real parts squared plus imaginary parts squared square rooted. Now you got your R. Plug that into star. Ooh, I was getting so carried away I forgot the time until I heard chairs banging. N sub s is now minus 2 over log base 10 of R. And now you could say, okay, do a ceiling function. I don't know if that's even the right symbol, but what I'm trying to say is take the argument and go to the smallest integer above that, and that's what capital N sub s is. So capital N sub s is the smallest integer exceeding the argument. Now we know how to deal with settling time, bullseye, concentric rings in the z-plane. We'll pick up with the others on Wednesday. Thank you for your patience.